Hey everybody, and welcome to a new exciting video in the audio signal processing for machine learning series. This time we'll be looking into Mel Spectrograms. This is a flavor of spectrograms that is extensively used in AI audio research and AI audio real-world applications. But before we get started into Mel Spectrograms, I want to give you an overview of what we did over the last couple of videos. And that is the short-time Fourier transform, and we also looked into extracting and visualizing spectrograms. Now, if you're not familiar with this concept, I highly suggest you to go check out my previous two videos, because what I'm going to say next in the video builds on top of those two notions extensively. Now, without further ado, let's move on to this visualization of a spectrogram. And as you can see here, on the x-axis we have time, on the y-axis as usual we have frequency, and each point, which is represented by a color in this 2D representation, tells us how present a certain frequency is at each point in time. The thing that I want you to understand here is that the frequency representation with a normal vanilla spectrogram is linear, and it uses hertz. And this is kind of problematic in terms of like the way we perceive frequency. Now, I don't just want to tell you that, I want to show you that. And to show you that, we're going to do like a little psychoacoustic experiment. So we have a couple of audio samples. So each of these has a pair of notes. So in the first one, we have C2 that moves to C4, C4 being the middle C note. So the C note at the center of a piano keyboard. In the second sample, we have G6 that goes up to A6. Now, if you take a look at the difference in the frequency mappings, or in other words, in the frequency expressed in hertz, between the two notes in the two pairs, you'll notice that more or less, like these two differences are the same, or almost the same. And that is around 200 hertz. But will these two pair of notes like sound the same in terms of like their pitch distance? So this is my question to you. Okay, so let's listen to these two pairs of notes. The first one, C2 to C4. Okay, the second one, G6 to A6. Okay, I'm sure you'll agree with me that the second sample has the two notes that are way closer in pitch than the first two notes. And this is a little bit weird, isn't it, right? So the difference in frequency as expressed in hertz is actually the same, but that isn't true from a perceptual perspective, because like the second pair of notes sound way closer in pitch than the first two. This basically means that the way we perceive pitch is non-linear, and indeed we have way better resolution at lower frequencies than we have at higher frequencies. Specifically, what happens is that humans perceive frequency logarithmically. And this is a little bit of a problem that we have with vanilla spectrograms. And that's because, as I said, frequency is expressed linearly in or vanilla spectrograms. And so we don't account for the way we human beings perceive it. Now, let's think about an ideal audio feature that we would like to have and would make like the most sense to feed to our own like machine learning and deep learning algorithms. Well, first of all, we want some kind of a time frequency representation, because we want to know how the different frequencies in a signal evolve over time. Then we want for this feature to have perceptually relevant amplitude representation. And this, once again, is because amplitude and the way we perceive it is logarithmic. It's not linear, right? And both of these things we can achieve with vanilla spectrograms, and indeed we have like log amplitude spectrograms, as we saw in the previous video. But what we can't achieve with vanilla spectrograms is the third aspect, which is perceptually relevant frequency representation. And this is what Mel spectrograms are all about, right? And they check out all of these three interesting conditions. But now, Mel spectrograms. So it's a term, it's a concept with two words. One is spectrograms, and by now you should be more than familiar with it. The other one is Mel. So what is this thing? What's a Mel? Right? This concept is connected with the idea or concept of a Mel scale. And the Mel scale is a perceptually relevant or perceptually informed scale for pitch. And here we have like a nice representation. So I suggest you like to focus on this graph right now. So on the x-axis, we have frequency expressed in hertz. On the y-axis, we have frequency expressed in mels. And this blue curve is just the mapping between hertz and mels. And as you can see, it follows a logarithmic kind of like function curve. And indeed, the Mel scale is logarithmic in nature. And by being logarithmic, what it does is it becomes perceptually relevant, perceptually informed. And what does this mean, really? Well, it means that equal distances on the scale have the same perceptual distance. Okay, let's try to understand this with an example. So let's say we have a couple of like pairs of notes. So the first one, the first pair is 500 hertz and 500 mels and 510 mels. The second one is 1000 mels and 1010 mels. Now, the perceptual difference between these the two notes in the two pairs is the same. So the pitch distance is going to be the same. And that's obviously not true for hertz, as we demonstrated with our little experiment earlier. Okay. Now, one thing that we did, that like researchers did with the Mel scale, is that they standardized it so that at 1000 hertz we have 1000 mels. Now, you may be wondering, but how did we arrive at such a perceptual scale? Well, we arrived at it in an empirical way doing psychological experiments. Now, and last question you may have regarding like the Mel scale is, where does the term like Mel comes from? Well, Mel is an abbreviation for melody, and melody, I mean, is very connected with the concept of pitch, because pitch, I mean, is the main thing that you have in a melody along with rhythm, I would say. And so like melody, mel, pitch, so you get the idea, right? Okay, but now let's take a look at how we can move from the frequency expressed in hertz to the frequency expressed in mels. And it's this like empirical like formula here, as it said, like found by trial and error with experiments. And the important thing here, apart from all of this like constants, is like the logarithm that we use. And indeed, we have like this logarithmic kind of relationship. Now we can take the inverse of this function, and with this, we're going to be able to move from mels back to hertz. Now, I want you just keep in mind these two formulas, because we're going to be needing them like moving forward. Okay. So now you should have like a basic idea of the Mel scale and why it is important in terms of like the way we perceive music, or not music, sorry, we perceive pitch in this case. Okay, but how does this relate to the Mel spectrograms? Okay, and here I'll give you a kind of recipe for extracting Mel spectrograms. And this recipe has 3 steps. So the first thing that we do is we extract the short time Fourier transform. And the second thing is to convert the amplitude to decibels. In other words, like we take like some kind of like logarithmic representation of amplitude. Now, as I said, these 2 steps are like the ones that we use for vanilla spectrograms. So nothing new here. The new thing is the third step here, which is converting frequencies to the Mel scale. So this is like the whole point of Mel spectrograms. So we take a spectrogram and then we convert the frequencies in that spectrogram to the Mel frequency representation. Okay, so the next question is, how do we do that? Well, for converting like these frequencies to the Mel scale, we have a bunch of like steps. It's like these 3 steps here. So we choose the number of Mel bands first. We compute the Mel Filter Banks. Now, don't be scared about like this scary word, Mel Filter Banks, because I'll show you what this is like in a few minutes. And finally, we want to apply the Mel Filter Banks to the spectrograms. Okay, so now I'm going to break down each of these steps for you so that it becomes like super clear how to do this. Okay, so let's start with the first thing. So choosing the number of Mel bands. Well, first of all, so Mel bands, so when you're just like reading some research, say in AI audio or music information retrieval, and researchers are using Mel spectrograms, one fundamental parameter that you have is the number of Mel bands, right? And that is like a parameter that can vary. So the question is like, how many Mel bands like should you pick? Well, 40 is totally fine. 60 is fine. Sometimes you find numbers like close to 90 or even 128. The reality is it really depends on the problem. There isn't like one single answer to this question. It's a little bit when you ask, okay, so what's a learning rate should you use? Well, there isn't just like one answer. You have to try out some different stuff and see what works best. And indeed, the number of Mel bands is a hyperparameter that you can vary and see the impact that it has on your algorithms, on your deep learning algorithms. But all in all, you see that usually like the numbers that we have is between, I would say like 40 and 120, 130 like maximum. And I mean, one thing like that's a little heuristic here is that if you think about the number of notes, for example, that we have on a piano keyboard, that is like 88, right? That is kind of like the way like we tend to like resolve like frequencies and we represent them. Now, the idea of a Mel band is like kind of like a range of frequencies like that are like perceptually relevant. So I would expect like that this number like makes sense because like they're kind of like close to like the notes that we usually experience, like for example like on our like Western music. So these types of numbers like make sense for that because they are comparable. They have like the same order of magnitude as the number of notes that we usually experience. Okay, good. So now we know like what numbers of Mel bands like to choose from, more or less. Now, the next step is to actually construct the Mel Filter Banks. And here we'll actually understand what these Mel bands are. Okay, so how do we construct the Mel Filter Banks? Well, this is a kind of like a quite complex process, or it's not really that complex. It's more like it's a multi-step process. It has like 5 different steps. And so I'm going to break down all of these 5 steps for you. I'm not going to get too much into the math here, nor am I going to like implement it, but I highly suggest you to try to implement all of these steps that I'm just going to talk about in a theoretical way, because that is a very good exercise to see whether like you understand all of these steps precisely. Okay, so how do we build like this Mel Filter Banks? Well, first of all, we take a lowest and highest frequency, like in the frequency like range and like in the short time Fourier transform that we've just kind of like extracted, and then we convert the lowest and highest frequency to a Mel representation. So how do we do that? Well, we use like this little formula that we already encountered before when talking about the Mel scale. Okay, so now we have like the lowest and highest frequency that we want to consider expressed in Mels. Next step. So now, given like we've already chosen the number of Mel bands that we want to use like for our Mel spectrogram, the next step is to take like the frequency range in terms of like Mel, the lowest Mel like over here, the highest Mel here, and then we want to create as many points, equally spaced points, as the number of Mel bands that we want to use. In other words, so this is going to be like very simple like to visualize. So let's say like we have like 6 Mel bands. We want to use 6 Mel bands. So what we'll do, if this is like the lowest Mel frequency and this is the highest Mel frequency, we'll just like take this point here. So we'll just create these 6 points and they'll be equally spaced in this frequency range here. Okay, now what we're gonna do next is quite simple really. It's basically just like converting these points back to hertz by using this function here that we found when we were talking about the Mel scale. Now, if you're wondering about this these points, so what are they? Well, they are the center of the different Mel bands. Okay, they are the center frequency of the different Mel bands that we are talking about here. Okay, and we'll see those like with a visualization in a couple of moments. Okay, next step. So we've now converted back like this center frequency points for our like Mel bands back to hertz. And now what we want to do is we want to round these points to the nearest frequency bin. So why is this like important? Also, why do we need to do that? Well, it's because we are dealing with discrete signals. And that means that we don't have like infinite perfect resolution like on the frequency. And actually like a resolution is somewhat like constrained by the frame size of the short-time Fourier transform. So what that basically means is that when we'll get back to this like center frequency points, we can't just like take them like as they are. We need to like bin them, and we need to just like round them to the nearest like frequency bin that we have available, right? And finally, we have the last step, which probably is the most important, which is like creating triangular filters. And these triangular filters are basically the kind of like the building blocks of a Mel filter bank, and they are connected with this idea of the different like Mel bands. So I'll visualize what these things are, and then I'll explain how we get like to this visualization here. So don't be scared about like all of this complexity, because it's way easier than it looks like. Okay, so here on the x-axis we have the frequency. In the bottom is expressed in hertz, in the top here is expressed in mels, and here on the y-axis we have weight, and weight is between 1 and 0. Why do we have a weight there? Well, because these are filters. Basically what they do is they just like tend to filter sound, and when you have a weight equal to 1, you're not touching like that signal. But with a weight below 1, what you are doing is just like dumbing down, kind of like dumping the signal, right? Because you're scaling it with a value that's below 1, right? Okay, so now as you can see here, we have an example with like 6 Mel bands, okay? And here indeed you have like 6 points like overall. And so these are the center frequencies for our 6 Mel bands, okay? And so let's take, for example, like this second point here. So this is, let's say like it's at 2000 hertz, which is 1526 mels. Okay, so what you can notice here is that the difference between all the center points for the Mel bands is the same when it's calculated in Mel. So we basically have always like the same difference between like two subsequent like center frequency points, but this is not true in the case of hertz. And that's the whole point, right? That's the whole point, because which like frequency expressed in hertz, when we go like towards higher frequencies, we have to just like spread out the frequencies to have like the same perceptual difference in terms of like frequency distances. Okay, but now let's focus only like on constructing a single triangular filter for one Mel band. Okay, so let's take like this point, Mel band number 2 here. So the center of this Mel band, as we said, is 1000 or 1526 mels. and then the lower end and the higher end so are taken by respectively taking the center of the previous Mel band and the center frequency of the subsequent Mel band. And for the lower end and the higher end of a Mel band, we have a weight which is like equal to 0. So in other words, like below this frequency, the lower end frequency, like we are not going to have, so the signal is completely muted, is put to 0. Same thing here for the frequencies above the higher end here. Okay, and now what we do is we kind of like trace a line between the lower and the higher end, and we connect that with the center frequency where the weight is equal to 1. And so if we do that, we actually build a triangular filter like this. Now, if you do the same thing again for the third Mel band, fourth, fifth, and sixth, well, you just come up with the whole Mel filter bank, right? And these are triangular filters, okay? And so I hope like you now have like an understanding of like what a Mel filter bank is. And the whole purpose of this beast is that then we can just like apply this to like a normal spectrogram, and then we can filter out like the different frequencies and convert them like to normal like, frequencies in hertz to frequencies expressed in Mels. Okay, but here we have just like a visualization of a Mel filter bank, but obviously like in digital signal processing as well as like in machine learning, we don't do operations with visualizations. We actually use math and linear algebra like most of the time, right? And so what this means is that we can represent this Mel filter bank using a matrix or a two-dimensional array. And the shape of this matrix is going to be like this. So like the number of rows that we're going to have like in a Mel filter bank is equal to the number of bands that we chose. In our example, it's going to be equal to 6, so 6 rows. And then the number of columns that we'll have, it's equal to the Nyquist frequency, or in other words, frame size divided by 2 plus 1. And so this is like the matrix that we'll be using for representing a Mel filter bank. Okay, so I hope you now have an understanding like of this Mel filter bank, and then now with all of this information, we need to go like to the final step in the conversion from frequencies to Mel scale for our spectrogram. In other words, we are actually moving from the spectrogram to the Mel spectrograms. And how do we do that? Well, we have to apply the Mel filter banks to the spectrogram. And how do we do that? And here linear algebra is going to help us quite a lot. Okay, so here we have like the shape of the Mel filter bank matrix. And now here we have the shape of another matrix, and this is the matrix associated to a spectrogram. So if you followed along like my last couple of videos, you know by now that the shape of a spectrogram, the shape of a matrix that represents the spectrogram is given like by these numbers here. So the number of columns that we have, the number of rows that we have in the spectrogram is equal to the Nyquist frequency plus 1, and the number of columns is given by the number of frames, or in other words, like the temporal bins. Now, so we said that the whole point here is to apply Mel filter banks to spectrogram. But what does that mean? So that must mean something in a mathematical way. Well, if you're familiar with linear algebra, you've probably noticed something interesting about these two matrices, and that's that the number of columns of the first matrix, or the Mel filter bank matrix, is equal to the number of rows of the matrix that represents the spectrogram. So when this happens, it means that we can apply like matrix multiplication. Okay, so in other words, applying Mel Filter Banks to spectrograms from a mathematical standpoint means multiplying, doing like matrix multiplication between the Mel Filter Banks and the spectrogram. The result of this multiplication is the Mel spectrogram. Now, I'm not going to get into the details of this matrix multiplication because it's outside the scope of this series. But if you're interested and you don't know that much about linear algebra, I have a video over here that you can check out where I talk about basic operations with like matrices, and one of those is actually matrix multiplication. Okay, so now let's take a look at the Mel spectrogram. So the Mel spectrogram is a matrix itself, and its shape is given by the number of bands. So we have like as many rows as the number of bands that we chose, and on the number of columns that we have is equal to the number of frames of the original spectrograms. Okay, so in other words, if you think about this, like this multiplication here, so applying Mel Filter Banks to spectrogram, what enabled us to do is basically to convert the frequencies just from hertz to Mel bands. Okay, and that's the whole point of a Mel spectrogram. And the cool thing now is that we are using Mel bands, which are kind of psychologically relevant in terms of the way we perceive pitch. Okay, but now let's take a look at what this means in terms of like a visual representation. And well, if you're familiar with spectrograms, well, Mel spectrograms are no different at all. So you still have a heat map, and that's because we have like a matrix, right? And on the x-axis we have like time, on the y-axis once again we have frequency, but this time like the different frequency bins are not like the linear bins that we used with the spectrogram, but rather the Mel bands. Each frequency bin is a different Mel band, which is perceptually relevant. And then each point that we have here has an associated color that represents how present a certain Mel band is at a certain point in time. So basically the conceptual understanding or visualization of Mel spectrograms is the same that we had for spectrograms. The only thing that really differs here is the way we represent a frequency, which is like pitch, like psychologically relevant this time, differently from a spectrogram. Okay, so the last question that we might ask here is, why should we bother like learning about Mel spectrograms? So, and the answer to this question is that they are extensively used in a lot of AI audio and AI music research. So a lot of papers that you may be reading about like audio classification uses Mel spectrograms. This is very, very true also for a lot of like music information retrieval, AI music papers. So for example, Mel spectrograms are overwhelmingly used like in automatic mood recognition, music genre classification, music instrument classification, and way more applications we have like, for this type of spectrograms. Okay, but this time we only focused on the theory of Mel spectrograms, and I hope that by now you have like a clear understanding of like what Mels are, the Mel representation, and why like Mel spectrograms are different than spectrograms, and why they are very convenient like to use in a lot of like the applications where like we're talking about audio and music. So the next time we'll be moving to actually some kind of like implementation. So we'll be extracting Mel spectrograms from audio files using Python and Librosa. And Librosa has a lot of like very nice utility functions that we can use that will save us a lot of time. And then we'll visualize Mel spectrograms. And then we'll also try to extract and visualize Mel Filter Banks so that you can actually understand and see how we can, just like represent them and what they actually represent. Okay, before I dash off and I finish, I want to remind you about the Sound of AI Slack community. And there, if you have like any questions about like this stuff, your projects, and way more stuff regarding like AI audio and AI music, you can just ask. And there you'll have like a community of people interested in AI audio, AI music, audio processing that are ready like to help you, ready like to share like their ideas, their projects. So I really suggest you to go check out this community, and I'll leave you the link to sign up to the Slack community in the description below. It's all for today. I hope you really enjoyed the video, and I guess I'll see you next time. Cheers.